started. So today I'm going to continue discussing sort of the empirical perspective, and we are going to start looking at markets with without transfers. So mostly education for today. But just sort of to motivate it, you shouldn't think about education as being the only one, or students' assignment to schools as being the only relevant application of what I'll talk about, but things like the medical match between medical school graduates and medical school and hospitals, something that Al Roth, of course, spent a lot of time on, kidney transplants and so on. Those are similar examples. The goal of the empirical exercise is going to be sort of similar as yesterday. So given some data and knowledge of the environment and knowledge of the mechanism, we're going to try to estimate primitives and evaluate counterfactual policies. As yesterday, what I'll emphasize is the role of information structure. So in particular, as we saw yesterday, there were a lot of crucial assumptions we had to do or we had to make so that this resampling method or some other way how to estimate the beliefs of players at the time the mechanism was played could have been consistently implemented. So same thing is going to show up today. And more importantly, I'll show you an example where actually going away, or rather doing away with rational expectations can reverse the ordering of the mechanisms in the counterfactual. So that's sort of where I'm gonna get. Key difference from yesterday, in these markets without transfers, is that typically we have to specify more complicated preferences. So there will have to be a little bit more econometrics today. You will see why, hopefully soon. And then we'll need to define a different metric than money. So typically in these environments, people use miles traveled. So the two examples I'll talk about today use that, but of course there are some issues with that, in fact, with interpretation, but I'll come back to that hopefully too. So just to set up the ideas, the canonical school choice problem, we're going to have I students and N schools, okay? Each student is going to have some ordinal preference ranking over the schools. At each school, they will have a priority. And again, we're going to be much more explicit what these things are, but this is the general formulation of the problem. So at every school, student I has a priority pi I j 0. Each school is going to have a capacity. So this is a vector of capacities. Again, in some applications, this might be actually finer because we're going to look at capacity for sort of free lunch students and not free lunch students and so on. But again, in canonical problem, think about just each school having one. And the school choice problem is then a tuple that is characterized by these three objects. And the matching in our environment is going to be a set of students mu j that is assigned to a school with the property that mu j students have to be the subset of the students that we have, and each student is assigned to at most one school. Okay? All right. Script M is going to denote the set of possible matchings, and then a mechanism is going to be a function that is actually going to be parameterized by these priorities and capacities that then takes whatever reports a student might make. Okay, typically, the space of reports is going to be the same as the space of rankings, and they map these reports into matchings. I will talk about it right now. So as of now, they're just parameters for our purposes, but I will. That's going to be important for us. Okay. So in practice, these priorities are exogenously assigned, and typically they are a course. Okay. So typically those are things like distance. Okay. So do you live in the neighborhood of that school? That's going to be one input into what priority you get. Again, I'm going to show you some functional forms for these priorities. That's going to be the key distinction between the various mechanisms that we'll worry about, okay? How these priorities are calculated and how the mechanism takes them into account. So, as I said, in many school districts, the priority is going to be a function of the distance to school, and typically, at most few other binary variables, such as do you have a sibling that goes to that school, okay? Few exceptions. This is much more common in Europe than in the US, but so in the US, there's only few schools that actually have an entrance exam. Okay, in Europe, let's say, this would be much more commonly used. Okay? So, given you have course priority structure, and schools really don't have preferences over students because there is no exams, so the only preferences that they have are going to come from these priority structures, they will be indifferent. So the way this is dealt with in practice is they're just going to run a lottery, a uniform number that is going to be tagged to these priorities to generate a strict order. Okay? Now, there's a literature on how to do that. This is something which I'm not going to talk about. For those who are interested, the Abdul Kadiroglu, Patak, and Roth paper is a good reference. All right. So many school districts use the student optimal stable matching algorithm, the deferred acceptance, where the students propose that most of you probably know about. So I want to just highlight two differences in interpretation from the canonical marriage market type applications of this. Okay. So first of all, here, as I've mentioned a minute ago, we have priorities rather than preferences on one side of the market. So basically, the school's preferences, at least in public school districts, are actually a policy parameter, which is important, which kind of has, at least I think, been kind of ignored. So in fact, this is something which the school district can pick. And the current, let's say, values of that parameter are set, it seems to be, based mostly on historical reasons, rather than some optimization as a solution to some optimization problem. So one thing to have in mind. And more importantly, perhaps we don't care about welfare on the school side per se. Again, this might not, suppose we thought there are important peer effects, then this statement would not be quite true, because actually we might care about welfare if we thought that schools can attract better teachers if they have better students, something of that sort. For now, I'm gonna ignore that. Okay. Again, we generally don't care about schools' IC and IR constraints, unless, again, which is an important question, which I don't think the literature addressed enough. Basically, that would involve thinking about some sort of a general equilibrium of the education market. So, could charter schools enter or private schools enter into this matching mechanism, or into this particular market in general? For those of you who know who follow this literature, there's a lot of empirical papers that actually show that charter schools typically have a discontinuously positive impact on students' performance in many markets. But kind of those papers are typically based off some sort of a regression discontinuity type of a research design, which completely ignores the fact that these charter schools have to siphon the teachers from somewhere. I mean, the teachers don't they don't come as a random draw from the population. The charter schools are good because they pay better and they get better teachers. So that those type of questions, again, typically have been ignored, but I think are very important. All right, so the playground, so from the mechanism design point of view, we have a lot to play with because we have a lot of data coming from markets that use at least these three different mechanisms. So as I've mentioned, deferred acceptance with student proposing is one that is very often used. Very often used is something which we'll talk about much more, something which is called the Boston mechanism. And infrequently, but something which I guess economists are rooting for quite a bit is the top trading cycles. So I'll briefly describe how these three work, but we will mostly focus later on the Boston mechanism because, as we'll see, these two, have truth-telling as a dominant strategy, whereas this one doesn't. And so the one question that we are going to be addressing is, okay, suppose I get some data on reports from a manipulable mechanism, so something where students can be strategic in submitting their preferences. Can we say something? So can we somehow recover true preferences? So that should be reminiscent of what we did yesterday, that we see bits. Bits in many settings are this combination of the true willingness to pay and that shading factor. So something like that is going to go on in here. Can we somehow use the characteristics of that mechanism, the properties of it, to recover the true preferences so that we can actually make statements about what would happen if we went to the deferred acceptance or something?
But it's well known that students are student's family is behaving in a manipulable mechanism like the Boston mechanism don't manipulate very well. I mean,
Okay, so hold on to that thought. Okay, so this is that's exactly where I'm gonna go to. So as I've mentioned before, one way to do that. Let me now jump ahead a little bit, but again we'll circle back. We can pretend that we are in some sort of a fully rational world where everybody knows everything and everybody knows outcomes, and we can construct some equilibrium condition like we did yesterday and try inverting. Okay, but as Eric is saying, this would be kind of foolish in this environment, given that it's so complicated that the families or parents rather probably don't know enough to actually make that sort of a calculation. So if they are manipulating this thing, it's more of like using some rules of thumb, which is potentially very far away from the optimal way how to manipulate the mechanism. And so when we are doing this inversion, we might want to allow for that possibility. Okay, so we will do that, and that's sort of one of I've started motivating this by saying that if you do away with the rational expectations and you allow something more perhaps reasonable in this environment, you might get an inverse ordering for particular applications of the mechanism. So that's exactly what we're going to be getting.
It's also known that in closed-form mechanisms, people manipulate.
Yes. So both of those things are known. So I guess the optimality is so both of those things are known. So it's fairly easy to see that there's a lot of incentives to manipulate, that people manipulate, but they don't manipulate optimally. So what we will do is we'll try quantifying these different effects, and so I'll show you how. By the way, there is a very nice review article by Porak in Annual Review that sort of describes these markets and what we know about them. Okay, so a quick summary of those three that I had in my playground. So, the deferred acceptance, such that again, for those of you who have never seen it, which probably is nobody. Is there anybody who doesn't know the deferred acceptance algorithm? Okay, good. It's really a room full of theorists. So, very quickly, everyone applies to first choice school. If that's over demanded, that school keeps as many applicants as it can up to the capacity, where they rank them by some score, which is a function of the priority. In deferred acceptance, it's exactly equal to that. And rejects the rest. Okay, people that are not rejected are provisionally held, and that's the key of the deferred acceptance. So in the next round, who was rejected applies to the second best school, but the school can now change their choice. Okay, so that's the key distinction between the next mechanism and the deferred acceptance. So in particular, in Boston, which is sometimes called the immediate acceptance mechanism, everybody applies in the first round to their first choice school. If that school is over demanded, it again keeps as many applicants as possible up to the capacity, where they rank them by the score, but they are immediately accepted. So basically, when we go to the second round, where a student that was rejected goes to his second preferred school, okay, at that point, that school might be out. Because even though that school might prefer him, that school might be out because it accepted too many students, or up to a capacity students in that round before, okay? And so now, what the key feature of this Boston mechanism that arises is that, if you are close to being indifferent between two schools, and so in particular, there is a school nearby that you like slightly less than a school that is further away, but you have this priority of getting in, you might now think about, should I maybe reverse the report that I'm submitting to the mechanism, because if I don't, there is a possibility that the school nearby is going to get full, and I will lose my priority. Whereas if I were to submit it as my first choice, I'm going to get in. So that's the reason why this sort of a mechanism is, going to be manipulable, or in other words, it's not going to have truth-telling as an equilibrium strategy. Okay, the top trading cycles, I'm not going to talk about it too much today, but the way it works is really that's this pointing mechanism. Okay, so we assign a count. So the version, typically the traditional top trading cycle starts with houses, where everybody has a house. In the student example, we assign a counter to each school. which again corresponds to capacity. And then we let every student point to their most preferred school, and every school to point to the student with the highest score, okay, that is available. Then there is a result that there has to be a cycle, at least one of them. We can remove that cycle, and we can continue this. And given this is a finite game, everything is gonna clear. That was a question?
Just given the circumstances you just described, where the student might have an incentive to misreport, that makes complete sense. But from the mechanism designer's perspective, is this actually a problematic deviation, right? Because it makes that student better off. Maybe there's reasons why we shouldn't think of that as a negative thing. I mean, obviously from the design.
Yeah, so I'll show you an example where actually manipulating is going to increase welfare. So allowing Boston is going to increase welfare, but there is plenty of examples where it goes the other way as well. So that's another one of those cases where, again, you have to turn to data to be able to answer that question. This is nothing where theory is going to be very helpful, because we know the theory allows us to understand the trade-off, but to evaluate that trade-off on a particular application is actually a function of the preference distribution and so on. Okay, so I want to start by talking about large markets first. Just because they are going to allow us to set ideas for these identification arguments using the data. So typically these mechanisms are described in terms of algorithms, as I did over the previous slides. And that sometimes is useful, but sometimes it might not be. Just for example, if you want to do some comparative statics, say in capacities or something, it might not be very easy using just the description of the algorithm to do that. And again, and also to know whether a given report is optimal in, say, Boston mechanism under some preferences, you would actually need to know what the algorithm would do for any other possible report. So the mechanism is easy because there you have the function. You just evaluate that function at that other report. You require that the utility at that other report be weakly less than the utility at the optimal report. Okay. So anyway, so the reason why I want to go to the large markets is that in those, and I'm going to talk about the specific paper, the intuition that you might want to have is that the ICE report is going to be sort of tiny. Okay, so there is not going to be the manipulation of ICE report is not going to affect the probabilities of other students of getting into a given school. Okay, so this is coming from a paper by Azevedo and Leshno, which talks about a particular way how you can think about the asymptotic so that you arrive at that sort of a economy. And the nice thing, which is something which we're going to use quite a bit, is that in that limiting economy, a stable matching can be characterized by a cutoff. Again, I'll characterize it on the next slide. And the way to think about this asymptotics in the Azevedo and Leshno is really that you hold the number of schools fixed, you increase the number of students, and you proportionally increase at a particular rate the capacities. So that's the type of a asymptotic that I want to talk about now. And again, the reason for that is going to be because I want to reduce this problem to something low dimensional, to just a vector of cutoffs. Okay. There is another, just for full disclosure, there is another asymptotic theory that Fuhito and Parak proposed and Konrad Menzel, which drives both sides of the market to infinity, which of course would be, for example, useful probably for marriage markets and such, but probably less for colleges. So going back to Azevedo and Leshno. So again, we have, well, now C, before we had I schools. Now I'm adopting their notation. We have continuum mass of students. Student is characterized by a type where, again, we have some sort of a priority and preference ordering. Sorry. Yeah. So this is a score. I call it score, but really you can think about it as the priority again. Colleges are going to prefer students with higher scores, so the E's are going to determine who is preferred by the schools. There is a technical assumption that colleges' preferences are responsive. We don't have to worry about that. Preferences are strict. And the continuum economy is then going to be a vector of positive capacities. and the probability measure over these types. Okay, so the key takeaway from this is actually this part. So at the limiting economy, every student is going to be facing a lottery of what school they're going to get into. Okay, because they don't know what other types they are facing. They don't know the realizations of these uniform draws that make the preferences strict. Okay, which essentially makes everybody uncertain about which school do I get into. But the uncertainty that you're facing, the lottery that you're going to be picking, is a function of what you report. Okay, so for simplicity, assume every student finds every college acceptable, and vice versa. And now there is these standard definitions of stability. So there's going to be a matching, there's going to be a blocking pair of a student and a college in a particular matching mu if the college prefers, given the preferences of type theta, if the college C is preferred to whatever the matching assigned to that student theta, okay? And either this assigned, either this, whatever was assigned to college C was less than its capacity, or it was at capacity and there was a student that was preferred less than theta by that college C. Okay? And then, of course, stability is defined that there does not exist a blocking pair. All right, so now to those cutoffs. So there's a nice kind of a duality way how to think about these cutoffs in terms of prices. So that's why they use this nice P notation. So imagine that remember we have a unit mass of consumers. So PC is going to be the cutoff or minimal score required for admission at C. D of P for a type theta is the most preferred college at which his score is above the cutoff. Okay, so otherwise the student remains alone. If there is no school such that he's above the cutoff, so if all schools were oversubscribed.
Again, why is there a minimum score for each college?
Okay, let me give you an example, and then I'll go back. Okay, so a score is going to be something like this. All right. So what is that? There's going to be a report-specific priority part, which is going to be determined by those scores priorities that I talked about. Okay. So for example, we can, without loss, make it look like this. So if I lives in the neighborhood and has a sibling, that's the highest priority. It's going to be 1. It's going to be 2 if you live nearby, 3 if you have a sibling, and 4 if you don't have any priority.
And this is set by the college.
This is set ex ante. This is exogenously given to the mechanism. But as I said earlier, there is no reason for it to be exogenously. It's a parameter that we might actually take seriously and start thinking about optimizing. But they don't do that. Okay. So basically, these priorities, together with then some random lottery draw and potentially other features that in particular, some function of the report ordering. They all put together are going to map into a score. Okay. Now the way I wrote it here, it would actually be you would actually accept guys with the lowest score. The way I wrote this function, right? The most preferred ones would be the guys with the lowest score because this is the most preferred one. So in the Azevedo and Leshno is the other way around. Yeah. Yeah, I'm not aware of any. I guess.
That seems so natural here. I mean, since it has such a large effect on the outcome.
Yeah. I mean, I don't want to say there is none. It's just, but I am not aware of any. Eric? Yeah.
So there is a score. So it says that why isn't the cutoff? Does the cutoff depend on the student's preferences?
In some mechanisms, what we are going to talk about here is we're now characterizing the general, matching possibilities or the set of possible matchings, if you want, in this economy. But so in the Boston mechanism, sure, as we're going to see in a little while, the cutoff is going to depend on the submission. I mean, whoever, because you can manipulate the outcome, the cutoff is going to depend on the report.
So are the cutoffs primitive of the model? Or
No, they are the outcome. They are derived. They are the equilibrium objects. The cutoffs are.
So there's a theorem here.
There is a theorem in this that's coming here. Okay? There's a theorem. So right now I'm just defining what a cutoff is. Okay? So aggregate demand for college C is the fraction of students that demand it. Okay? So again, remember we defined the demand of type theta as the school that is most preferred, subject to the constraint that you are above the cutoff of that school. Okay, so now we are aggregating all these types that are above the cutoff. And then P is going to be a market clearing cutoff if it satisfies these two conditions. So that's where it's going to come from. So either it has to be that the school is undersubscribed, in which case P is 0, or if P is bigger than 0, then it must be that it's in capacity. It's at capacity. Okay? And now what particular cutoff you are going to pick, well, that depends on this condition. And so now the theorem, which is a very nice theorem, well, there's a theorem that arises out of this analysis in Eduardo's and Jakub's paper. First, to get to that theorem, we can define a matching using that market clearing cutoff. Right? So in other words, I can take the most preferred school at the vector of these cutoffs and define that as a matching that the student is matched to. Okay? In the same way, I can take pretend I have a stable matching, and I can define the associated cutoff as the lowest score that the student that was accepted to that school has. And now clearly these two are inverses of each other. Okay? It turns out that these arguments actually translate into finite markets as well. And again, the good intuition that I would have for this is very similar to like a pricing game, where you can think about these cutoffs as prices and there being excess demands or not at a given price vector.
What do you mean by translate into finite markets?
I mean that, if you took a sequence of finite markets, you would limit to this in some sort of a... All right, so the theorem, and again, I'm not going to show it, or prove it rather, but what Azevedo and Leshno show is that this continuum economy has a unique stable matching, which is a very strong result, except for knife edge cases. Okay, so if we think we have an economy that is discrete economy, which is reasonably close, say the New York schools, to this environment that you have many students, and a few schools, but capacity is large enough that everybody can be accommodated, then sort of this gives you a good intuition for what you might want to look for in the data. Okay, so this is the statement that I just answered to Stephen. So they show that as the finite economy grows large, these market clearing cutoffs are going to approach this price vector that we talked about before. And again, why is this useful? Well, because now this very complicated thing can be characterized by a low-dimensional object. We have only C cutoffs that we have to worry about to characterize basically the whole system.
And so that means, regardless of what kind of stable matching you are using, you will have a unique cutoff.
Say it again. I couldn't hear.
I mean, so that means no matter what kind of stable matching outcome is, and you will have a unique cutoff.
Yeah, well, no matter how, I don't know what you mean by no matter how stable, which stable matching you have, there's a unique one here.
Sometimes it's, if you are using college optimal or student optimal, maybe you can have multiple equilibrium stable.
Not here. There's a unique one.
But I know that in
The matching rule is fixed.
matching,
Well, it's not going to matter. There's a unique stable match. So even if you went both ways, you would arrive at this one. By the way, this is a fairly well-established empirical fact as well. That sort of, if you look at these, Al has a sequence of papers on that as well. That sort of there is very few actual empirical data sources in which, if you were to move between a student optimal or a school optimal deferred acceptance algorithm, you would arrive at a different stable match. Okay, for example, I have seen the residency hospital matching, residence hospital matching data, and there it was like less than 0.01% of cases in terms of sort of how frequently it was run that you could get, or sorry, there was less than 0.01 doctors that would be changed between the two matching mechanisms. But here, this is irrelevant because we have just one stable match. Yes?
So, going back to the definition of stability, I don't see how any matching can be stable unless every student gets his or her favorite school. Because couldn't you always just, if you have a given measure of students, couldn't you always just accept one more and not change the measure of students that are in your school?
No, but you have to report. The DP was defined. You have to be above a cutoff, right?
Right. So I understand how this case works, but going to just the general definition of stable matching, schools are always going to have room for one more student.
Yeah, but it's a zero match. You can allocate one.
Yeah, that's not going to change the capacities, right? So one student you could move around, but that's not going to change anything. Okay, so the goal now is to take this observation that you can characterize the set of stable or the stable matching by these cutoffs. What can we do when we have data from these mechanisms? So again, the nice thing about these settings is that we will observe agents' applications submitted to a mechanism rather than just a final match. I should have said, there's a paper by Nikhil Agarwal in the AR that tries to infer preferences of one side of the market just from the outcomes. But that, of course, comes at a cost. You have to make a strong assumption on, like, everybody sharing the same preferences, or vertical preferences on both sides of the markets, kind of, and that sort of stuff. So I'm not going to talk about that. But so in most data that I am interested in what we're going to talk about, we will see agents reports. Okay. And on top of that, there will be good variation coming from, the realizations of these lotteries, because again, the data comes typically from the school boards. The priorities, so you know everything about the student, and sometimes even some demographics, which is actually going to be important, like things like distance of a student to all schools, whether they have siblings, something maybe about their families. Okay, and so this combination of things is going to allow us to answer questions that just the outcomes we wouldn't be able to answer. All right, so what we're going to is what we're going towards is this environment where we will need a demand system. I've mentioned that before in order to evaluate, say, the different mechanisms. But there is plenty of questions. There's plenty of questions that you wouldn't need to go that far. So in particular, because we have these random lotteries, there is a lot of papers that make use of this sort of experimental design, randomness design, that you compare students that barely got in and barely didn't get in, and you can sort of talk about what happened to their wages, later college outcomes, and so on and so forth. So this is like an ideal, source of variation for all kinds of labor papers. Okay. But if we want to talk about what would happen if we were to change the whole mechanism, if we were to change the priorities, and so on and so forth, we need more. Okay. And again, one thing that maybe wasn't obvious, but hopefully will be obvious from an example I'll have soon, the Boston mechanism, the reason why it can sometimes be better for, even though it's manipulable, it can be better in a welfare sense for the students, is that it allows them to express, in some sense, intensity of their preferences, right? Because as I have given this example with me living in a neighborhood where I have a school that's just slightly worse in my perception than a school that's further away, I might actually invert in my report the ordering of the two schools. The key point there is that it's just slightly worse. Right? So basically this Boston mechanism allows you to evaluate how close to indifferent you are and change your report based on that. Okay? So we'll see that, all right? Okay. Yeah. So one other point that I want to make in terms of, again, the mechanism design of these markets, very often, rather than choosing priorities per se, very often what the mechanism designers or school districts in this case are interested in is the impact of their mechanism on things like desegregation, things like opportunities to low-income families. So those are sort of the objectives that they would like to satisfy somehow. But there is very little known which of these mechanisms might achieve which of these objectives. All right. So I think there is a lot of potential both on the theory side and for sure on the empirical side to try to address these.
I didn't understand how you tease out the intensity of the preference. I don't know.
Well, you will need that demand system. So that's one of those things. So we will have to specify a utility and basically allow people to have different utilities in some sort of a space. And then we will have some metric between utilities, not necessarily money metric, but some other metric in utilities that is going to allow you to compare two schools. And if the utilities are going to be close, the cardinality is going to be important.
Yeah, on questions like desegregation, a school could capture a goal of desegregation through the way it assigns priority.
I completely agree. In fact, Chicago does that. Parag has a paper on that now.
It's a little bit more complicated because now
The Supreme Court.
well, there are legal restrictions, possibly, but also for the school itself, it can't evaluate individual students anymore. It has to, or a student's priority will depend on the other students that the school has accepted. But in principle, can't you use this mechanism to study these mechanisms to study the effect of segregation and then you switch from one mechanism to another?
I agree. So again, that's why I'm motivating it. So basically, if you are going to start with the current mechanism, you invert back to get the utilities, you can start playing around with the priority system and so on and so forth to address these sort of things.
I thought you said that it hasn't been done.
Yeah, people haven't done it. I'm not saying it's impossible. That's why I'm putting it on slides right here, because this is something which is fairly straightforward, in fact. If you can, but again, we're back to what we talked about yesterday. The central bank has a hard time formulating their objective function. I think school districts are no different. Okay, so there is some vague understanding that this is important, but to what extent is that important relative to other things? Who knows? And this might actually vary district to district. But I completely agree that if you give me as a goal, we want to have a certain fraction of racial composition in the school district in every school, there is a fairly easy way how to redesign the priority system to get there, I bet. And we could then use what we're going to do. So where we're going, again, is we're going to start computing welfare in, say, the distance metric. But then you could do it in that counterfactual world where we run deferred acceptance under those different priority systems or whatever and compare the welfares. There is, again, nothing too complicated. The complicated step, which I'm about to explain in a little while, is how to invert in this manipulable mechanism the observed reports, which are just ordinal, into these cardinal utilities, into these utilities in some sort of a space that you can then compare and make welfare statements on. Okay? Okay, so the paper that we're going to go through, or we're going to sort of draw the results from, is by Nihil and Paolo. And their data comes from Cambridge, which runs a variant of Boston mechanism, really. So Cambridge, Massachusetts. as I've mentioned a couple times already, the big question is whether we can invert this submitted reports, which are just ordinal, into something which we can make statements on and useful, which we can use for counterfactuals. So let me just state it as a fact that students respond to strategic incentives. And the way you can establish, for those of you who are interested in that, you can just go and look at the paper, but the argument is fairly simple. You just look at people that are very close to, so by the way, the Cambridge mechanism allows you to rank up to 3 schools, and you have the neighborhood priority for schools, the 2 closest schools to you. So it's not based on some geographical areas, but literally on distance from where you live. And so you can then look at what's the school 2 and 3 closest to you, and where this difference changes, and compare students around those, and you are going to see a big discontinuous difference in how people rank schools. So that shouldn't be there if it wouldn't be for the strategic manipulation of the reports.
Why, I don't understand. Why strategic manipulation for this continuation?
Well, normally you would think that there might be some distance preference and so on and so forth. That would be, school that is further away from you, you would like less and less. And now all of a sudden I'm comparing 2 students that are exactly the same distance to a school, but one of them loses the priority and the other one doesn't. And you see a big difference in the probability that they're going to rank a given school first or second.
But who says that only the distance determines the majority? You said that the different students have the same function.
Take everything else out, okay? So condition on everything else but the distance, and do that experiment. That's sort of what this is doing. The regression discontinuity. Okay, so now I want to tie it back to the Azevedo and Leshno because we will work for that. So now, as I've given you this this function before, it's without loss. I'm now going to say schools prefer lower scores. Okay, so you can just take a minus in front of it. So again, we're going to have a vector of cutoffs, and you're going to be matched to a school that you rank the highest if your score is below the cutoff, and the cutoffs are such that the capacity constraints hold. If a school is oversubscribed, there is a positive cutoff. Otherwise, it's 0. Well, it's 1 in this case. So what Agarwal and Somaini do on top of the Azevedo and Leshno is they actually extend this cutoff characterization to this report-specific priority world end cutoff. So in the original Azevedo and Leshno thing, we don't have these additional pieces. But hopefully that it's clear that that's not going to change anything. Okay, and so what Eric asked before, there is a function that maps the report, or somebody else asked, G maps the report and the exogenous priority type to some number, to a vector, which is a number for each school, which determine the score of that student for that particular school. Okay, so again, if you live far, you're not going to get that priority boost. If you don't have a sibling in a school, you don't get a sibling boost, and so on. So for every school, you get this number. Okay. On top of that, to every number, we're going to get that uniform dot. There is infinitely many ways how you can sort of construct this function G. This was the one that I showed you before. That's just one example. All right. So again, we are going to. This is the exact priorities in Cambridge. Each program, the way it works is that, so this is a parameter of the mechanism. Each program submits a capacity. It's a little bit murky how this gets chosen, and on top of that, you would think that this also can be actually adjusted ex post, which is something that also happens, but that's something which we typically abstract from. And each applicant can submit an order list of up to 3, in our case, schools. Then we have this function G that maps these priorities and these reports in this particular way. So the way I constructed it here is that the rank is much more important than the priority. That's what the Boston does. It really matters which turn you submitted the preference in, which round you submitted the preference in. And ties are going to be broken by that uniform draw. Okay, so everybody clear on how this works? Yes?
But the RSP form, this is a feature of the real world institution?
Yes. So this is going to be, so they have, it's slightly different in Cambridge, but again, as you can see, the point is that it results in that ordinal, on that ordinal ordering. So whatever way you are going to construct it, as long as it preserves the ordinal ordering, it doesn't matter. So this is, you know, now you can, in this environment, there's an easy way how to think about the Boston and deferred acceptance. Boston basically takes kind of lexicographically the rank and then the priority, whereas the deferred acceptance just looks at the priority. Okay? So I promised you an example with the Boston outperforming the deferred acceptance. And the key, again, you know, the key comes from us having the utilities. Okay? So we are going to have this. So the example is as follows. It comes from a paper by Attila. We have 3 schools. Each of them have a capacity of a third. Students can be of 2 types. One that really likes school 1 much more than school 2, slightly more than school 3. And another type which is sort of much closely, you know, that likes school 1 more than 2, but not as much. And so the key is this difference. Okay? Now, it turns out that this type is slightly more likely than the other. Okay? So now what happens in this world? Under student optimal stable match, so under the deferred acceptance algorithm where students are proposing, well, it's, you know, dominant strategy to submit your report truthfully. So we're going to submit 1, 2, 3. If we are type 1, if we're going to type 2, we're submitting 1, 2, 3. For everybody is submitting the same thing. Okay? Which means that what are we going to get? Well, with probability, if we are the first type, we're going to, with probability third, the school 1, it's equally likely we're going to get to either of the schools. So type 1's expected utility is 5/3, type 2's expected utility is 5/3 as well. Okay? But now you can see that this clearly, you know, it's not going to be efficient. Right? We would want to have type 1's, as many as we can, put in school 1 and type 2's in school 2. So what does the Boston do? Well, again, truth reporting is not going to be an equilibrium because we can improve upon the deferred acceptance allocation. And the way we would do it, if we are type 2, we would say we prefer school 2 more than school 1. Right? So imagine we submitted, one way to do that is we submit a report 2, 3. What happens then? Well, everybody of type 2 gets placed in school 2 because there is only a third of them. There is a seat for all. And then we have 2/3 of people left, so they're going to be equally split between school 1 and 2. Okay, so what are the expected utilities? Well, with probability half, I'm getting 4. And this guy, with probability 1, I'm getting 2. So both types are now getting 2. So 2 are better than 5/3. So Boston does better in this environment. Okay. So now that example is enough to actually hopefully to convince you that it's not dominant strategy to submit truthfully. And you know, we constructed that example to show that Boston can be better, but there are examples in which it is worse. But again, the intuition gets to do with the Boston mechanism allowing you to express this intensity of preferences to some extent, whereas the deferred acceptance doesn't.
So here Boston does better at equilibrium.
Yeah.
So it assumes strategic behavior by the agent.
Sorry?
It assumes strategic behavior by the agent.
Yeah. So indeed, we are looking for an equilibrium of that mechanism. Okay, so going back to the data now, we're going to start with, yes?
Is there a sense in which we know if the example you constructed of the Boston mechanism is generic?
No. So there is examples going either way, as I have said. So, you know, it's certainly, you cannot make any generic statement. At least I don't think you can. Okay, so Cambridge has this explicit diversity goal that I wanted to also mention, which is that basically they split the capacities into a capacity for students that qualify for free lunch, so something like below some income level, and students that don't, so that they have to pay for the lunches. This is a typical sort of way how you identify poverty. The funny thing is that the capacities don't have to add up. Okay, so there is a total capacity that the school has, and then there's a capacity set aside for free lunch and for normal students, but the free lunch plus no free lunch doesn't have to add up to the capacity. It can be more, so that they want to have some leeway, presumably. I don't know. That's a fact. As I've said before, even exposed, there is a little bit of wiggle room because they say what the capacity is, but then they add 2 seats here and there, and that's a little bit of a mystery how this gets decided. And
It's been known for hospital resident matching that hospitals have historically reported lower capacities than the true ones. They have higher residents. So maybe.
And so for hospitals, I would just add that, for those of you who know that literature, there's this issue with couples. And there's theorems that sort of say that if you are allowed to expand capacity by 1 or 2, I guess, is it 2, I think, then, there's a stable match which solves the problem even with couples. Anyway, so there is a good reason in hospitals, presumably, to allow some leeway. I'm not sure in this case what is the rationale. Okay. Yeah, so just to give away the result, and we're going to work our way to it, it turns out that the mechanism that these guys are running, if we compare it to a deferred acceptance, which we'll do by the end, we're going to see that this is better. So this result that we illustrated by means of that example, that the Boston mechanism can increase utility, is going to be at work here as well. Okay, so bear with me, we're going to get there. But so the trouble is that we don't really know what that means, right? We kind of can say it does better than the deferred acceptance, but whether this is actually peanuts or whether this is something important, who knows? Okay, so that's one problem with this other metric that we have to work with. But more importantly, perhaps, this ordering becomes much less strict once you relax this rational expectation assumption. So let me go to how this actually works. So we talked about how this mechanism works. Let me skip this part. So what I want to use this table for is just to illustrate that there is good reasons to manipulate the mechanism in Cambridge. So what you can see here is that this is the 13 schools that are in that neighborhood. The important row to look at for those of you who can actually read it is this first rejected row. Okay, so P is the proximity priority. So if you are in that neighborhood, the first rejected student in Graham Parks, which these two are the most elite schools, let's say, okay, is actually in the first round, and he had a proximity priority. Okay, so if you are living close to this school and you have a sibling, you're fine, you're getting in. If you don't have a sibling, well, you already are facing a probability distribution that you're going to get in. Okay, if you wanted to go to Haggerty, it's actually this is I guess regular. So this means that I don't have any priority. I don't have any proximity priority. If I were to rank Haggerty first, the first rejected student is going to be a guy with no priority, but who ranked the school in the first round. And so this is what's going to create that problem. Right? So I know if I were to rank this school first, I'm going to get in. Well, assuming that the results in next years would correspond to what we see here. On the other hand, so I might prefer Graham Parks by a little bit, but there, even if I live nearby, I might not get in. So if I am kind of almost indifferent between Graham Parks and Haggerty, if I rank Haggerty first, I'm going to get in with some probability. Because if I live nearby, for sure, if I don't live nearby, with some probability. And so at the end of the day, what I'm going to do, what I should report, depends on how I think about these priorities, how I think about these probabilities. Okay? So takeaway, there is scope for strategic manipulation of these reports. Oh, and I should have said, the scope differs for the poor or for the free lunch and no free lunch students. So the free lunch students get into everything from the top schools. Okay, they don't in some other schools, which sort of suggests that there is segregation, at least based on income, already, because there's too many of them applying, in some sense, to some other schools than the 2 top ones. Okay, so here is the key thing. So as I said, we have to be a little bit more specific about the utility. So we're going to write down a utility function which is going to say that a student I's utility from attending school J is going to be a function of, some preference parameters. So some random coefficient beta, let's say, some school fixed effect, some characteristics of the students and school, like distance between them and so on and so forth, and some random component. Okay. So the assignment probabilities are going to be determined by the mechanism and other students' reports. So again, those are going to be random from the perspective of the students. You don't know the epsilons of the other guys. Potentially you don't know the beta i's of the other guys. So you don't know what they're going to rank. You might have some ideas about their distribution. So we're going to look for a Bayesian equilibrium of this weird mechanism, of this Boston-style mechanism, assuming that students know the number of students of each priority type. Strong assumption, which we might want to relax later. But do not know the lottery draws. And once you think about it in this way, the relevant condition for us for this Bayesian equilibrium is going to be that if I'm going to submit a report Ri, the dot product between the probabilities corresponding to that report and the utilities, so this is a vector of my Vij's, okay, got to be bigger than the expected utility from submitting a report R prime. So straightforward definition. What it turns out that this definition allows us to characterize in quite a nice way, let me skip this part, what space these V's must live in, okay? Because what we have, each report now corresponds to a vector of probabilities that you're going to get into a school. So that BNE condition, this inequality, has to be true for every report, which means that these V's that rationalize the observed report must live in a convex cone. They must live in a space that's bounded by these lotteries, by these planes that are characterized by these lotteries. Okay? So V's that are optimal for R have to satisfy this object, this inequality, which is exactly a convex cone, okay, in that RJ space. And this is a very useful characterization because this allows us then to think about how we can parameterize these V's and potentially get their distribution. Yes?
So to refine
Mm-hmm.
is V the vector of reports?
Yeah. No, okay, V's are the utilities.
Okay.
Those are the primitives. That's what we want to get. R's are what we see. Okay? So V's, everybody is endowed with V's. Sort of in the previous notation, this was theta. That's the type of a student. Okay? And R is what that student is going to report. So in the deferred acceptance, he would report the ranking of these V's, truthfully. In the Boston, he might not. So it's going to be an ordinal report, right? Mm-hmm.
We were discussing before that student families may not be optimizing very well. Where is that going to be? That possibility captured?
It's going to be captured in how we're going to construct these probabilities. Okay? So under rational expectations, we're going to impose that they know the distributions of the V's, right. They know the priorities, and they're going to compute the true probabilities of these lotteries. Right. Under some other assumptions, like some adaptive expectations, for example, you might imagine plugging in there probabilities from last year. Okay, what's the probability that you would get in given where you live? You could do that experiment. Another would be I can integrate out some types of everybody and take like an average of the probabilities associated with each lottery. So you can play around with it. These three are what Nikhil and Paolo do. Now I'm running slightly late, but sort of in that last paper that I want to talk about, they actually do something more. They parameterize these beliefs and use a survey where they elicit them to somehow do this experiment with actually what families presumably are thinking. And that's where we're going to get that reversal. Mm-hmm.
So
The Bayesian-Nash equilibrium here is a strategy that maps a type into a report, which, by that example that we shown and by the table that we shown, is not going to be truth-telling. So it's going to be a manipulated report, potentially for some types, truthful report for some types. But that's sort of the object we're looking at. Crucial, again, we're kind of relying on that Azevedo and Leshno statement that there is a unique one, right? So anyway. I'm going to skip the identification part just in the interest of time. The basic idea that for those of you interested in econometrics is that if you have something that shifts around this object, these probabilities, okay, independently of the utilities, so this would be like big changes in the priority structure or something of that sort, you can sort of imagine, changing this cone. So doing it very fine way you would take the intersection of the cones so that you get an identification of these V's. So that's sort of the intuition for how this actually works with data, okay? Even though in reality, typically these instruments are not as good to do that. Yes?
This means you're trying to identify the causal effects, right? You are trying to extract the causal effect of something that shifts the preferences. What's the meaning of identification?
Identification means if I give you the reports, can you recover these? So causal, I don't know what you mean by causal here. We don't talk about causality here. What I mean is that, okay, this gives me a set of these that are rationalizable, let's say, by the observed reports, but that's a lot of them. So now in order to narrow it down by identification, what I would mean is that is there a way how I could narrow down this set to a point? Okay? And so I just told you an argument that in theory would work. If you give me a lot of movements in these probabilities, in these differences, I will take an intersection of the resulting convex cones and end up with a point. Okay, briefly how to go about estimating this, because that might be that's related to what we talked about yesterday. So we see report Ri, there are all possible other reports. And what we want is as you've seen on that previous slide, we need the estimate of this to evaluate this object. So again, it's these probabilities that we don't know. So we can do, again, this resampling argument that we did yesterday. We can pretend that everybody, let's say, is symmetric up to that priority. So everybody living in a given neighborhood is the same. And we can start resampling I-1 other students with replacement and simulating thereby a different state of the world, different vector of population preferences. That's going to result in different lotteries corresponding or probabilities of getting into every school. And we can then simulate the mechanism and get the allocation. Okay. So, one comment on that: when you're doing this resampling, you are totally relying on the rational expectation part, because again, this is exactly as in the auction world. We're thinking everybody's playing the same equilibrium. I mean, we are drawing a different type. We're assuming that if I drew the type that Eric has, I would play the exact same strategy that Eric has. So that's the type-specific BNE that we talked about. Okay. On top of that, if I had some crazy beliefs, again, this wouldn't work. Because if my beliefs are I will never get into whatever, Hegarty or one of the schools there, this is not going to result in consistent estimates of my beliefs. So the V's that I would be recovering by following this procedure would be wrong. Okay? So this procedure would work only under those rational expectations. Okay. Yeah, and so the assignment probabilities, yeah, I've talked, this is sort of an argument for why reducing this problem to that vector of cutoffs is as useful. Because there is a very, very high dimensional problem of sort of these assignment probabilities are a function of each of those priority types, possible list of schools. It's sort of a very complicated calculation, but if you have these market clearing cutoffs, it's very easy. Okay, you just compare the resulting priority with the cutoff you're getting in or not. It doesn't depend on, when the market is big enough, it doesn't depend on what you report. Whereas if in a small market, the change in the report could change the cutoff and so on. So that's where that sort of trick comes in. So in terms of actual implementation of this, they parameterize everything. They parameterize the utilities, and they normalize so distance is one of the well, I guess I pulled it out here, but distance is one of the covariates, and we're going to normalize its coefficient to -1. That's going to introduce that metric on welfare that we talked about. Because now, once we have done that, if we can recover, say, these parameters, and say we have some parametric assumption on epsilon, we can now simulate the mechanism under any alternative rules. Okay, and then just compute the utilities for every I that mechanism allocates to that I, and sum across I's, and basically difference across the two.
Are there any other metrics that people have tried to use?
Not that I'm aware of. So this is something which I would definitely like to see more of, just because you would think, in the same way as we think about in the demand analysis, people might have different price elasticities, and people typically allow price elasticity to, say, vary with income or something like that. You would think that people have different distance elasticity. Some people like walking, some people don't. And so the fact that we translate everybody to the same metric clearly, doesn't sound like without loss. So that's a very good question, and something which
Some people like it and some people don't like it. That's fine, right? But your problem is if it's correlated with income.
exactly. So if it's correlated with some of the other axes, then. So in this case, depends on what the axes are. Yeah. Okay, so the way the actual estimation works is through Gibbs sampling. I don't know if you guys heard about that, but it's actually a very nice sort of Bayesian way how you can solve fairly complicated problems. So this is a very, very complicated issue, right? So we're trying to recover a lot of parameters. Okay, there might be some variances of these error terms. There might be a lot of these fixed effects and these fixed effects and parameters on the covariates. And so to write down a likelihood, in particular in a case where V is only set identified through that cone, might not even be feasible. So the Gibbs sampler allows you to augment the data and sort of say, okay, let me make a guess that I have a V. Okay, and again, I have a fairly straightforward argument why that's easy to get, but suppose we guess a V, so we augment data with a particular realization of V's, and then we start iterating through starting with a prior. By this augmenting data, we look at the posterior and we iterate basically one parameter at a time. Okay, so these are the parameters in the utility vector. These are the variances of the error terms. Then after we have updated those, we update each component of the V vector itself. Okay, and again, this is not a very difficult step, because once you have these parameters, the convex cone tells you that the V has to live in an interval. So that's not that difficult to solve for. Typically, you start with a normal with particular functional forms.
Can I ask you something?
Yes.
When you first wrote down the model, it looked like a random coefficients model because you had I indexes on the data. When I look at the formulation of the V's, I don't see any I's in the deltas, so I must be misreading something?
No. The delta.
Are they common across the individual?
So this I took from there. So maybe at the end of the day, for data reason, there is no reason why I wouldn't, so in principle, in theory, it's easy to add in an I on the delta. In practice, it would blow up the parameter space. So I think that basically for data reasons, they just don't do it. But in theory, there's nothing difficult. The identification is everything is gonna go through. It's just that the finite sample problem doesn't allow you to do it in the actual practice. So finally, I'm at some of the results. So what I want to basically point to is this line, okay? So what we have done is we have recovered, well, first of all, this line and then compare this and that, okay? So what we have done is we recovered these V's, or rather we now have a distribution of these V's, so we're going to take the means as a point estimate. So we have V's for everybody. So we can now, we have a V that corresponds to a report. Okay, so we have done that inversion. So for every report, we now know the true V. So therefore, if we have 1,000 students or whatever, we can now recompute the mechanism under deferred acceptance and get new allocation of students to schools. And we have the V's, so we can compute the welfare. Okay, and so we can compare the two. And so what you get is basically, so let's focus on this one. Okay, so this is this column, the three columns are what's called sophisticated. So basically that's taking into account that these students are manipulating. So that's doing this inversion in the way we talked about. This would be the calculation if we took the Boston mechanism as a truthful submission. Okay? So if we look at this manipulated reports, we get that if we were to switch to a deferred acceptance, we would actually lose welfare that's equivalent to like 0.07 miles traveled. Again, what this really means, I don't have a good idea, but it basically says we don't want to switch to deferred acceptance. These guys they by optimizing, they somehow are able to express the intensity of preferences better, and they do better. Okay? Having said that, the free lunch guys, they would benefit. Okay, so either they don't do their optimization as well, or there is some other reason why they're losing in the Boston relative to the deferred acceptance.
Well, this is an intuition that less benefit being strategic.
Yeah, we saw that in that table. They are getting almost everywhere. But, yeah, so that's, but if there is no benefits of being strategic, there is also no reason to be worse off. So, right, so then the question is, what is that something? Okay, now I lost myself, sorry. Okay, so as I said, so the benefit of Boston mechanism relative to deferred acceptance is actually positive, it seems. And there is actually other papers that find approximately the same numbers. Okay, so the bottom line, as I've said yesterday, I've mentioned that I don't think the payment mechanism, payment rule per se, matters as much as these other details. This is another example of that sort. That sort of, going to some other mechanism at the end of the day, in the sense that this is a small number. There might be some benefits or some losses if you switch, but that's probably not it doesn't look like a first order issue. Now, Paolo and Nihil try to change that resampling algorithm, and I've sort of talked about it a little bit by using probabilities from last year or some other small departures from BNE. What this does is that this becomes even smaller. It still remains positive, but becomes smaller. So let me finish in the last 10 minutes just by briefly talking about this other work, which basically argues that, well, the way you are thinking about these beliefs is really key. So what these guys do is they go, sorry, Afghanan?
Can you straighten me up on something? If I recall correctly the results from matching, and I might not, deferred acceptance when the students are proposing, right, gives the best for them, for the proposers.
The best stable match, yes.
The best stable match.
Boston matches are
Not necessarily stable.
Okay, so now you get a result that the Boston gives you better. So what's going on?
Well, by finishing that argument, the only thing you can conclude, it's not a stable match, what you're going to result with. Because if it were, then it would contradict the fact that the deferred acceptance results in the best match. So it's possible. The example that we showed before, the simple example we showed was also.
Now, the reason I'm confused is because, okay, you get the Boston, they're playing a Bayesian equilibrium. don't have a coalition that's deviating. Okay. You don't have a coalition.
Well,
It's not immune
It's
to
pairwise.
coalitional deviation.
Remember the coalitions that the deferred acceptance algorithm looks at are coalitions with the other side, with
The other
schools.
side, yes,
So
right.
implicitly,
This
you're
is
taking
not
into
here.
account the schools.
This is not
factor
here.
too.
Right,
This doesn't.
right, right. Not making a coalition with another school.
Okay, so they look at New Haven, but same thing. It's almost as Boston. They reverse just the ordering of the priorities in their construction of the report-specific priority. But the basic idea, it's the same mechanism where it might be worthwhile for the families to misreport. But what they do is they go out in the field and they try to figure out how parents actually rank the schools. So that's sort of an additional piece. And you can then ask yourself, first of all, are they anywhere close to rational expectations? So, given I know how many kids there are this year and I know what the priorities are the perceived probabilities that they are reporting to me anywhere close? The answer is, of course, no. And then if they are not, then if we were to take that into account, how are our calculations, welfare calculations in particular, going to change? So basically, if we do the Agarwal and Somaini again, except taking into account that the beliefs might be wrong, by informing how wrong through a survey, do we get a similar or a very different result? And I've told you a bunch of times already that the result reverses. Now, whether this is a general statement, again, we have to be very careful because this looks at New Haven rather than Cambridge. The demographics in New Haven is very different than in Cambridge. So there's all kinds of reasons why it might not reverse in the Cambridge application. So you should view this really more as a possibility result again, that we don't have sort of a general statement. Mm-hmm.
Is it possible that some maybe agitated parents might have more optimistic beliefs because of the screen negotiation process that you say does perhaps occur in practice?
Well,
In which case that might still be consistent with rational expectations, just that the game that you've modeled doesn't have that after procedure negotiation.
I would say that for few parents this is possible, but it can't be
Not
possible for that many parents that we're gonna see are wrong. Uh-huh.
So is the intuition here basically that if you're misevaluating probabilities of getting in, then when you sort of misreport thinking it'll help you get in, you're sort of only shooting
Exactly.
yourself in the foot?
Exactly. That's exactly right. So I'll show you a table on that because that's just a straightforward calculation that you can do. Sort of lining up the survey with the actual probabilities, and if the survey preferences were truthful, assuming then what they actually did result in a worse allocation than if they were reporting what they report in the survey. We see that about 30% of parents do that, which is very huge.
Now, doesn't this bring up the question of whether people would misreport even if we had a mechanism where it should tell them?
Yeah, well.
Should we do surveys and ask people in New Haven what they would do if we used?
Yeah, that's a very good question. So indeed, I would say we assume that in deferred acceptance everybody is rational again, because we assume, as in a second price sealed bid auction, that sort of you submit your value.
This we're off here. What makes us think
Yeah,
we get that?
I agree. So in some sense, I guess the argument I would take away is something like that: investing in information provision and providing tools to the parents to be able to evaluate these probabilities in a more reasonable, and whatever that means, way, is more valuable than changing the mechanisms per se.
I think there is evidence that the medical matching residents claim that this is a non-trivial number of people who truthfully report.
And that's a very educated group.
I've seen people present evidence that a higher percentage of people than you might guess misreport their preferences.
How do they? Well, we can talk about it later. It's hard. Yeah. Okay, so first thing you can take away from the survey: beliefs are all over the place. So it's not like rational expectations is even close, because at least there, we should have the same. If we have the same priorities, we should have the same perception of the probabilities. We don't. Okay. And this is the important part. So for low SCS households, which is pretty intuitive in some sense, they are much farther from the truth. Okay, so they are just really lousy at evaluating these probabilities. And finally, the subjective beliefs reported in these surveys, they actually do predict households' behavior. But as we have just discussed, not always. Okay, so I'm going to be a little... So this is the distribution of the beliefs from the survey. So the truth, okay, so the definition, we're going to define something with, like optimism, which is the true probability, the reported probability minus the true probability. And this is the histogram of that. Okay, so you see that for about maybe 50, I don't know what this is, 20 something % of people, this is about, they get it about right. Okay, but for most people, they're all over the place. Okay, so this sort of tells you rational expectations are probably not the way to go. Okay? Even though on average, maybe you might be right. So this is now going back to that question that we had, the discussion we had before. So if we define revealed strategic as, parents maybe rather than students who had a first choice different from their stated most preferred school. So those are the guys who we see writing down something else on the survey than in the reports. We have about over 50% students doing that. Okay, so again, strategic manipulation is a big deal. More importantly, this mistaken strategics, students who would have gotten to their top choice had they reported truthfully, it's 30%. So this is a huge number. Okay, so this then tells you immediately that the way they're optimizing can't be sort of the B&E.
So is it possible to take away that deferred acceptance is probably better than the busting because it gives people less room for strategizing?
Well, that would be a takeaway after we run this mechanism on this data. Almost surely. Again, though, assuming that in deferred acceptance they would understand the mechanism and report truthfully, which is something which is not quite obvious how we would guarantee. Yeah?
I don't know, a bit of ambiguity. It would be right to nudge people to report truthfully, just write somewhere, please report the true type. And if not the true type, please report the true preference.
So I guess this is a question more to Al than to me, because I'm pretty sure he did that in the medical match many, many times, that, telling them, look, this is a doctor optimal deferred acceptance algorithm, so you guys really, really should be telling the truth, and yet if we have evidence that they don't do it, it's hard to believe that it's going to work here. Okay, but anyway, so the bottom line here is that, okay, even if we want to implement this strategic manipulable, mechanism, what's important is to give these parents some tools that they can evaluate these probabilities properly. Okay, so and maybe help them with their decisions. So given I have just last 2 minutes, I'm going to go directly to this, to the results from the paper by Kapoor, Nielsen, and Zimmerman, which the two columns that I want to focus on are the last two. So basically, the second to last is the computation of a deferred acceptance minus the New Haven algorithm. So exactly what we did in the Agarwal and Somaini world in terms of miles traveled. But now you see that there's no minus. So in all, this is because we have distributions now. Okay, so this is the quantile of the income distribution. We get that the deferred acceptance, let me just make sure that it's income, so I don't remember. Anyway, so across the board, though, we get that the deferred acceptance is better than the New Haven. So it's exactly inverse of what we had. And in fact, so what they do on top of that is now if we ignore the survey, so ignore the fact that, so what they did, the way they implemented it is they parameterized beliefs. They allowed for some sort of a bias that they modeled through this shift factor, okay? So if we ignore that shift factor and we are back to the Agarwal and Somaini world, we get these negative results again. So again, it looks like in that world, the strategic manipulation results in an improvement in welfare overall. Okay, so that's kind of, again, to wrap up, this should hopefully convince you that the way you think about the beliefs is really important. So, whatever robustness notions or stability, some stronger notions, maybe even locally in terms of what these families believe, has very important repercussions on how we then come up with recommendations if we use data to conduct counterfactuals.
One thing that kind of bothers me about this discussion is that it's not clear to me why the concept of stability is relevant.
Oh, yeah, well.
In the sense that the schools are not free. You know, the schools have a priorities, and those really dictate the way they should. In short, a school cannot come to a student. I mean, a student and a school cannot hook up together after the algorithm has.
But here we didn't talk about stability too much.
Together, and the school does not have the liberty, you know, to say, okay, I'm going to kick out someone else because you prefer me and I prefer you. The priorities really dictate how the school should behave. So it's not clear to me the notion of stability is relevant.
But remember, the calculations we did were in terms of welfare and equilibria. We didn't worry about stability here. It's about stability. You know, you might worry in the residential match market because of unraveling and issues like that. Here,
this is not a criticism of what you did. It's just a question about whether the notion, to what extent the notion of stability is relevant in the context of schools and students.
yeah, I agree with you. I don't think it is too much. But I mean, again, it's the only thing where we used stability was in that limiting world of Azevedo and Leshno to characterize everything in terms of the vector of cutoffs.
It's tangential to your talk. It's a question to the matching literature, if you wish, in the context of schools and students.
Yeah, I don't think anybody stresses stability in that world.
I thought that was always the.
No, because Boston, it's always sort of comparing these different mechanisms, and it's well known that Boston doesn't necessarily result in a stable match. So it's more about, okay, what does the mechanism get us, and can we compare welfare across the different mechanisms? Much less about, do we worry about not getting a stable match, exactly for this reason.
The attraction of Gale Shapley is that it's strategy proof, not that
Right.
it results in stable match when it comes to
School.
schools.
Mm-hmm.
Different.
What do you mean by stable proof? Strategy proof?
It's strategy proof for the students.
You submit truthfully.
In other contexts,
Sorry?
like in the medical match,
Medical
have
match.
used
Yes, in the,
stability as a
exactly.
motivator.
No, in the
Yes,
medical,
the
there's
medical-
definitely,
in some specialties,
stability
there
does
was-
matter.
There was terrible unraveling.
Yeah, because of the unraveling mostly. That was the lawyer cleric
That's a
market.
big difference between
Yeah.
that
Mhm.
context
Yes.
and
That's
this
exactly right.
context.
Yep.
Okay.
Yeah, one more.
That Google both those papers treat beliefs and objective function of a student as getting into the best school, because what I would infer from pre-lunch people being segregated away from top schools is that they might be afraid that curriculum is too hard or something like that, and that their graduation rate might, which they presumably more likely to maximize, will be lower in.
But that should be subsumed. If you were to write down this preference function, this utility function in some sort of a flexible way, that should be subsumed in there. So, for example, you might imagine if these coefficients are a function of income, they would just have different, weight on the fixed effect of that school. And in fact, I'm pretty sure that both of those papers use fixed effects, school fixed effects that's interacted with the poverty status.
Yeah.
So that would address exactly what you're talking about.
The question is whether survey addressed.
Well, survey conditions on the income status, so they know the income of those. So you can for sure address it. I cannot remember whether they did address it in the estimation, but it's something that you could do.
The question more of perceptions, which might be more differentiated than just income status.
So that's a different. So that depends on the data, what demographics you would have. But there is nothing conceptually different from what we did in that environment. But I agree with you. There could be other dimensions than income. Education of the parents, for example, that would be an important determinant that we haven't talked
Probably
about.
something unobservable which complicates things in estimation.
Yeah.
Like
Yeah. So they, as I said, they parameterize this, so they have some randomness introduced in there. But okay, so great. Thank you very much.
Thank you very much.